Hi everyone, welcome to meeting number 16 of the M2D2 series. Today we are excited to have Derek with us. He will be talking about how to expose the limitation of molecular modeling, molecular machine learning using nativity clipped. So a bit about Derek before we start. Derek van Tilborg is a PhD candidate in the molecular machine learning group at the Eindhoven University of Technology. He primarily works on applying graph neural network for drug discovery. By leveraging his academic background in both biomedical sciences and bioinformatics, he works on bridging the gap between computational method and preclinical experiment. Thank you, Derek, for accepting our invitation and for taking the time to present this. Without further ado, the floor is yours. Thank you again.
Thanks for the lovely introduction. So let's start right away. So as you know, drugs are important. Modern medicine is truly centered around drugs, and for finding new ones, new and effective drugs is pretty crucial. However, as you also know, molecules are pretty complex, and human intuition about molecules has its limits. After all, we are just apes with iPhones. So we can benefit a lot by leveraging the power of machine learning for helping us understand molecules better. So examples for leveraging machine learning to accelerate drug discovery are, for example, de novo design, where models generate new molecular structures from scratch, or molecular property prediction, where you're predicting something about the molecule, for example, bioactivity of a molecule on a specific drug target, something that I'm very interested about. And molecular property prediction is used across the whole spectrum of early drug discovery. So it's really, really important. And at the heart of chemistry lies this idea that molecular structure determines its chemical properties. And a natural extension of this idea is the principle of similarity, where similar compounds have similar properties. And this concept of similarity is really the backbone principle of a lot of molecular property prediction. And while it kind of works, this principle is not bulletproof. So it doesn't always hold. So in some cases, very slight structural differences can cause drastic changes in complex molecular properties like bioactivity, for example. So what you're looking at right now are two molecules that are almost identical. They only differ by one carbon atom, and still the bioactivity of one of these molecules is a lot higher than the other one. And this big change in the structure activity landscape is called an activity cliff. So we have these small structural changes that cause huge changes in bioactivity, and they can be very annoying, especially during lead optimization, for example. So here, you don't really want to introduce big changes in bioactivity when you're optimizing a molecule. But on the other hand, these very specific changes are actually a gold mine of information on the structure-activity relationship of a model. And you could say that a model that can predict the changes in bioactivity on these structural alterations very well can be seen as a model that also models the structure-activity relationship very well. So this means that activity cliffs can be seen as a kind of a proxy of understanding this relationship. However, machine learning models, they kind of tend to break down in the presence of activity cliffs. They really struggle, quote unquote, understanding that. But it's unknown which strategies are best for dealing with them. So you might ask, is this actually a problem? Well, yes. Activity cliffs, they pop up everywhere, really. So if you, for example, look at a few commonly used screening libraries for molecular property prediction, there's a very high number of molecules that are very similar in structure. So in some libraries with curated drug-like compounds like Adenine premium, for example, you can see that almost half of the molecules in there have at least one or more lookalike molecule. So it is a real problem, and these activity cliffs they are everywhere. But yeah, well, now we know that models they struggle with modeling activity cliffs, and we also know that this is actually a real problem, but we don't know what the best practices are for dealing with this problem. So naturally, the following question arises: why do models break down, and where? And which machine learning approaches work best for handling data with activity cliffs? So to answer this question, we did the following. We gathered and curated a lot of typical drug discovery data sets. We then determined activity cliffs, and we explored a wide range of machine learning strategies, including classical machine learning strategies and deep learning models, working on graphs, for example. And we evaluate all these approaches on bioactivity predictions on activity cliff molecules. So starting, of course, with the data. So we collected and curated bioactivity data from Campbell. I'm pretty sure most of you are familiar with Campbell. It's a big database of compounds. And we collected data for a comprehensive set of drug targets. So in total, we collected data for 30 relevant drug targets. And we only use data with bioactivity annotated by KI or EC50 because well, these are arguably the most robust measures of bioactivity. And in the end, we cover almost 50K molecules. And the aim of this set of data sets is to mimic typical drug discovery data sets with different sizes, different targets, ranging from kinases to GPCRs to nuclear receptors, for example, really mimicking the typical scenarios. But before we can do anything really, we need to have a proper definition of these activity cliffs. So in the literature, they are often defined as pairs of structurally similar molecules that exhibit a large difference in their biological activity. And this is a rather vague concept, because what even is structural similarity, and when are two molecules similar in structure? And then what is a large difference in bioactivity? This second criteria is actually the most easiest to answer, I would say. So the literature tells us that somewhere between a 10x and a 100x difference can be considered as a large difference. And well, a 10x difference is already quite relevant pharmacologically. So we just went with that. So that was a pretty easy thing to answer. But then comes this similarity, and similarity is a lot more difficult to precisely define because there are many ways of determining structural similarity, and different methods of determining structural similarity. They also result in different activity cliffs, of course. So it's also pretty crucial to get this right. But also we know that there is no one set way of doing this. So we try to use a well-rounded approach that looks at similarity from a few different angles. So we use the substructure similarity, then a kind of similarity that looks at the scaffold, and a Smiles-based similarity. So starting with the first one, substructure similarity. This is a very general similarity metric that is used all over the place. I'm pretty sure that a lot of people are familiar with this, the Tanimoto similarity. So what you do to compute this is first you vectorize a molecule into a binary vector, for example, using extended connectivity fingerprints. And then you find the similarity between two of these bit vectors by calculating the intersection of a union of these two sets. And then you have a general substructure similarity. Then secondly, we used a slightly different approach that specifically detects similarity between scaffolds. So here we compute an atomic scaffold from a molecule, and then we calculate the Tanimoto similarity between atomic scaffolds. And finally, we use a slightly different kind of similarity based on SMILE strings. So as you might know, it is possible to represent a molecular structure as strings, as SMILE strings. And you can then calculate the edit distance, which is also known as the Liebenstein distance, between two of these SMILE strings. So what you're doing here is you're measuring how many edits are required to end up to go from one string to the other. And you can use this kind of distance measure to capture insertions, deletions, and translocations of compound fragments, which is something that's not very well captured using the other two approaches.
Hi, Derek.
Hi.
Did you try to use a measure of similarity that account for the 3D structure of the molecule?
No, not really. No.
Okay, and don't you think like it's kind of critical in understanding activity cliff, or just because of the limitation?
Yeah, I think it is important, but 3D structure is also something that's pretty difficult to deal with in some machine learning strategies. So because we're comparing a lot of different approaches, we thought, well, it's probably not the easiest route to go with 3D similarity as well. But I agree, it's quite important, and it could be a nice addition actually to these three methods.
Okay, thanks. And there's a few more questions from Dom and Oscar.
Yeah. Hello, Derek. So
Hi.
I had a question very similar to this about the 3D structure. So I would like to know for the activity cliff, is this something like that is really related, in your opinion, to the molecular graph, which is an incomplete representation? Like when we have two molecules that have a high activity cliff, is it typical that their 3D structure or their electronic densities vary a lot, or usually they are also similar in these terms, but we still observe an activity cliff?
Yeah, so there's no straight answer for this. So in some cases, yes, there are also some papers that try to quantify this, and they really look at this 3D structure or the electron density even, but this isn't always the case. So it's pretty difficult to put your finger on what exactly causes these cliffs sometimes. But it could indeed be similarity between electron density, yes.
Okay, and if you have two molecules that exhibit an activity cliff against a specific target, does that tell us anything about an activity cliff against another target? Or not really? Is the activity cliff target specific?
Yes, it is target specific. So maybe there are some more general rules here, but yeah, I would say it really depends on the target.
Derek, I have a couple of questions, very quick questions. The first one is, have you tried to use matched molecular pairs to define an activity cliff?
No, we haven't. I know it's some papers have taken that approach, but we didn't. Yeah, so no, we haven't tried.
And the second question, maybe you will talk more later, but it's about how you make sure that your activity data is high quality enough to say that your activity cliff is not an experimental error and it's a real activity cliff.
Yeah, so that's something that keeps coming back, of course, with all computational things you do. So we got our data from Campbell, and maybe you know there's always a bit of junk in there. So we try to filter out some of it, but mean, it's not perfect. I know that, but also if you start to remove everything, of course, then you have no data left. So it's always like a difficult balance to maintain here. But yeah, there is probably some junk in there. That's just the reality of dealing with public data.
Okay. Thanks, Drew.
To Oscar's point, don't you think that maybe taking into account because I think in some of these data set you have some molecule that have been measured multiple times, and you have kind of the experimental error. So maybe taking into account the experimental error of every experiment in defining the activity rate, instead of saying 10s the activity, we can say 10s like the standard experimental error that we observe like over this data set or something like that.
Yeah, so we used that to filter out a lot of data from Campbell. So not for all cases, but for some cases there are multiple data points available. And then I think we said like, oh, if there's more than one log unit of standard deviation, we kick them out. Don't remember exactly what rule we used there, but we used the variation to filter out some stuff from the data. Yeah.
Cool, thanks.
Okay, so to wrap up these three different approaches of similarity, we come to this definition. So we define activity cliff as having at least a 10x difference in bioactivity and a 90% similarity at least one of these three similarity metrics. And we use this kind of approach because they all capture slightly different things. So if you look at this example over here, you can see some activity cliffs that are specific to one of three of these similarity metrics, and they all kind of capture different elements of similarity. So now that we've defined activity cliffs, we can compute them on our data. So that's what we did. We determined activity cliffs on our data. And of course, the nature of activity cliff is always pairwise. And because these cliffs occur in a pairwise fashion, it makes comparison to predictions on non-cliff molecules a bit complicated. So what we did is we defined molecules that exhibit any cliffs as an activity cliff compound. And we used that information to split our data set, where we distribute based on the structure and on it being an activity cliff compound. And then you end up with 30 split data sets ranging from something like 3,000 training molecules to 600 odd training molecules. And just like the screening libraries I showed in the very beginning, you can see that some data sets, they contain a substantial number of cliff molecules. So, okay, as a reminder, the question we want to have answered is, which machine learning approaches are best for dealing with data that contain activity cliffs? And again, we are going to compare quote unquote old school methods and some deep learning methods. And one of the hypotheses of using deep learning approaches is that they might be able to detect cliffs better because they can learn more complex relationships, right? But before I get ahead of myself, let's start with some of these classical methods first.
Derek, sorry to interrupt here, but before you dive into the modeling, I didn't understand the splitting strategy here. So for a given target, you take 80% of the data that is not an activity cliff, just the standard training data for this. And then of the data that you do have activity cliffs, you split them together as pairs, or you split them separately?
So splitting is actually, it's really difficult to have a good distribution of cliffs between train and test, because a lot of these data sets, they contain like compound series. So a compound can have a cliff with a lot of different other compounds. So having them like separated as pairs is it's really impossible to do. So what we did is we use stratified splitting to make sure that there are activity cliff compounds both in both the train and the test set, but we weren't able to make sure that they are paired because that wasn't possible actually to do that.
And did you do anything to separate the train and test via the sort of diversity or scaffold or something like this? Because one of the biggest challenges with ML on some of these things, right, is that you end up basically memorizing the the training data, and your test data is sort of irrelevant if you've sort of split randomly.
So we first clustered our data into I think we used k-fold clustering. I can't remember it properly, to be honest. But we clustered our data, and then from every cluster we did stratified sampling to distribute the cliffs over train and test. Okay. So that makes sure that you're dealing with this scaffold problem that you mentioned. Okay. Then the modeling. So these machine learning typically operates on molecular descriptors, at least the more old school, quote unquote old school methods. And there are two main types of fingerprints or of descriptors: binary fingerprints and classical descriptors. So we export 4 commonly used descriptors that are based on distinctly different approaches. So 2 binary fingerprint approaches we use were ECFPs. So these are radial substructures, and MACs, which encode predetermined fragments. And then we also use WIM descriptors, which describe the 3D shape and size of a molecule, and just regular old physicochemical properties like the weight, log P, number of hydrogen bond donors and acceptors, etc. And coupled to these 4 descriptors, we use commonly used and well-respected machine learning algorithms for molecular property prediction. So we use random forest, gradient boosting, support vector machine, and very simple KNN. And to optimize these, the hyperparameters of these models, we use 5-fold cross-validation and grid search. So using this combination of common machine learning strategies, we predicted the bioactivity on activity cliff compounds in our 30 data sets, which yields almost 500 different models to analyze. And this resulted in the following. So on the y-axis here, you can see the RMSE on activity cliff compounds. So this is the prediction error of the log10 bioactivity on activity cliff compounds. And what becomes obvious immediately is that these binary fingerprints, so the ECFP and the MACs, they really outperform the other descriptors. You see WIM is the worst. Physicochemical properties are a bit better, but still worse than the binary fingerprints. And this pattern and order of descriptors is the same for all algorithms. And this tells us that the descriptors are doing most of the work here. If we do a global ranking based on the activity cliff RMSE, we see a similar pattern emerging. So what you're looking at right here is a PCA, but it's scaled between the best and worst performance for every method. So we added the column containing the best and worst performance for every method, and then we did the PCA. And then you will end up with something like this, which is a scaled PCA that also contains kind of semi-quantitative information about your method performance. So you still see which one does worse than the other one. And you see a very similar pattern emerging over here. So methods, they are clustered by descriptor and not by algorithm. And the best one is a support vector machine with ECFPs, and the worst ones are well, anything using WIM, really. But of course, looking at the performance of the Cliff compounds only is just part of the picture, right? And we want to know how well is the performance of Cliff compounds compared to the overall performance. So by comparing the performance on Cliff compounds and overall performance shows that they are highly correlated. So models, they are slightly worse at predicting bioactivity on Cliff compounds, but models with a good overall performance, they also indicate overall better performance on Cliff compounds. But there are some outliers here. Okay. So what about deep learning? So I hypothesized a while back that maybe these deep learning methods, they are a bit better at capturing these activity cliffs because they can also capture more complex relationships in the data. So what we did is we explored two main approaches: deep learning models based on graphs, molecular graphs, and models based on strings, small strings. So starting with molecular graphs, unlike, for example, images, molecules, they are quite difficult objects to digitalize. They all have different sizes and shapes, which is quite difficult to deal with. And one way to solve this problem is by representing molecule as a graph or as a network. And here nodes in the network represent atoms, and edges in this network, they represent bonds. And every element in this graph, so both the nodes and the edges, they can have feature vectors that describe their properties. So for example, atoms, they can be encoded by their atom type, number of bonds, hybridization, etc. And bonds, they can be described, for example, by their bond type or stereo configuration. And to learn from this graph structure, from this graph structure data, you need a specific type of deep learning algorithm called graph neural networks. And there are many flavors of graph neural networks, but they all share a similar idea that information from neighboring nodes in this network is shared between nodes in a stepwise manner. And graph neural networks have been proven very effective for some molecular prediction tasks, especially for quantum mechanics. There's quite some hype around them, as you might have noticed. And this does result in a kind of a wild growth of algorithms. So what we did is we took three very popular algorithms from seminal papers and one method that has state-of-the-art performance for molecular property prediction. And they all take a slightly different approach. So the message passing neural network, they passes information from neighboring nodes by transforming it with the learnable function, and then graph attention networks, GATs, instead of a message passed across edges. This algorithm learns attention coefficients that determine the importance of features. And then you have graph convolutional networks, which is maybe the first big GNN architecture, and it aggregates information from neighboring nodes using a convolution. And then finally, the attentive fingerprint method uses attention mechanisms at both the atom and the molecule level. And we used Bayesian optimization for all of these approaches to optimize the hyperparameters. Okay. So besides graph-based approaches, we also explored string-based approaches, which are especially popular for generative models, but they can also perform molecular property prediction. As you probably know, you can represent a molecule as a character string by linearizing it. And then you can one-hot encode this sequence of characters. And there are a few different deep learning architectures that can learn from these sequences. And two popular algorithms that have been used before on molecules are CNNs, convolutional neural networks, and LSTMs, non-short-term memory. And CNNs are usually used for images, of course, but you can use the one-dimensional variant to learn from sequential data. And a recent study leveraged this algorithm on small strings with great success. And then you have the LSTMs, and they have been highly successful for sequence data and have also been used for molecule generation. And LSTMs that lend themselves very well for easy pre-training as well. So that's also something we did. We pre-trained all LSTM models using next token predictions. And then we used fine-tuning to tune this pre-trained network on the specific data set. So we use these commonly.
One question before you move on.
Sure.
So the graph-based method, you are not using pre-trained representation, right? You actually train them. Okay. And then the smile one, you are using pre-training. Is there any reason why you didn't kind of use Bayesian optimization for those as well?
So the reason, so there are two questions here, right? Why didn't you use pre-training for GNNs, and then why didn't you use Bayesian optimization for the other ones, right? So the first question, we did try it, but it didn't seem to help very much. So a lot of these pre-training strategies for GNNs, they are not very well established, and some of them, well, they're just not suitable for molecules, at least not very well. So we played around with that for a bit, but we didn't see real improvement, so we didn't use that. And for the sequence-based approach, we didn't use Bayesian optimization because we used the hyperparameters from these specific papers. That so, yeah.
Okay, thank you.
Okay, so that brings us to 180 deep learning models on activity cliff performance. So to compare between these classical methods and the deep learning methods, we included the best classical method, which was the support vector machine using ECFPs. You can see that on the bottom right in this box plot. And what becomes immediately obvious is that the simple descriptor-based method, they really outperform all the deep learning-based methods. And besides, the graph attention method performed so poor, well, it just performed very badly compared to the other deep learning-based methods, which all kind of performed in the same ballpark. But all of these deep learning methods, they had a very large standard deviation between data sets as well. And for a final comparison, we also added a simple neural network that just uses ECFP fingerprints, which is on the right. And it really highlights the power of using these descriptors, because it outperformed all the other neural network-based approaches.
Derek, I have a question.
Yeah, sure.
I have a question on the pre-training that you were doing for the sequence-based model. So were you only using the molecule from your training set, or were you using another corpus of molecules to do that?
We were using all of the molecules from the training set to do next token prediction.
Thanks.
Okay. So I also want to, if you can remind me how many data points there are in each of the data set that you tried for activity cliff.
Yeah, that really depends on the data set. So some data sets, they almost have 3,000 training samples, and some only have something like 600, 700. So it ranges quite a bit.
Okay.
Varies quite a bit.
And did you observe that either like the deep learning or standard machine learning model suffer more from the problems of activity cliff when you have smaller data sets than when you have larger data sets?
Good question. If you don't, I have a slide on that actually. So if you don't mind, I will answer that question in a few minutes.
Yeah, okay. You can continue the presentation then.
Okay. Cool. We have the box plot, and then we also did a global comparison of these methods using the same PCA approach. So again, this PCA is scaled between best and worst, and it shows very similar picture to the box plot. And by the way, we left out the results from the graph attention network because it was just the worst across the board, and it skewed the results of this plot immensely. So we got rid of that to make this plot a bit more interpretable. And what you see over here is again these descriptor-based methods. They are just the best, no doubt about it. Then you have these SMILES-based approaches, these sequence-based approaches. They are slightly better than most of the graph-based approaches. So yeah. But then again, only looking at the model performance on activity cliff compounds is just part of the story, of course. So we also checked its relationship with the overall prediction error. And here a similar picture, the classical descriptor based approaches emerges. So models, they tend to struggle a bit more on activity cliff compounds, but the error on activity cliff compounds and overall error is still highly correlated. And again, we see a lot of outlier cases here. So we, of course, were wondering like if there are some clear explanations for cliffs being more difficult. So one of the first things that came to mind is maybe it's due to the drug target. So we checked if it was, but that doesn't seem to be the case. So there are no clear trends visible here that point towards this direction. And then we also thought about the data set size. So we figured that data set size might influence the performance on activity cliffs quite a bit. But that also didn't seem to be the case. So we do see a trend here that especially the deep learning methods, they experience a lot more variance between data sets that are smaller. But this didn't prove to be statistically significant. So yeah, it doesn't seem to be the reason why actually. So we're still a bit in the dark here. So after evaluating almost 700 different models on activity cliffs, we now know a lot more about the behavior of models in the presence of activity cliff. But the question still remains, like, which machine learning strategies are the best for dealing with activity cliff? And the answer is, it depends. So in many cases, there's actually quite a high correlation between the performance on activity cliff compounds and the overall performance. But in some cases, this just isn't the case. So if you look at the global picture, you can see that while correlation is a pretty good indication, there's a lot of case-by-case variation here. And this variation is not exclusive to poorer models, but we also notice that it happens with the very well-performing machine learning strategies. So two models, they might have a similar overall performance, while having large differences in performance on activity cliffs. So this means that it's probably a good idea to test if your model performs well on activity cliffs specifically. So this brings us to the conclusion. So we saw that deep learning methods, they do not necessarily hold up yet against the simpler machine learning methods for drug discovery. And the model performance on activity cliff compounds resulted to be highly dataset dependent. So what does this mean? So first of all, we need to develop more efficient deep learning models that can overcome this inherent limitation of drug discovery. For example, dealing with small data sets. But this is not related to activity cliffs per se. Important nonetheless. Secondly, to get better models, it's probably a good idea to focus on the ability of your model to capture the structure activity discontinuities like activity cliffs better. And finally, we notice a big case by case difference in a model's ability to deal with activity cliffs. So it's a good idea to start measuring a model's performance on activity cliff molecules. So especially when you are trying to deploy a model for prospective applications, this is important knowledge to have. And to facilitate this last point, we developed a tool to measure a model's performance in the presence of activity cliffs, and it's called molecule activity cliff estimation, or MoleculeACE for short. And using this tool, you can systematically benchmark the performance of a model on activity cliff compounds, and you can compare it with these well-established methods that we evaluated. You can also use it to evaluate the chosen models on a new data set that's not included in our benchmark, and you can use it to further expand the definition of activity cliffs based on specific use cases. So while we provide what we think is a pretty general way of looking at activity cliffs, it's probably not perfect, and there might be some things missing. So you could expand this definition as well for your own use. And you can get this tool on GitHub for free with this link over here. And finally, if you are interested in our study on activity cliffs, you can find our preprint on Chem Archives. So that brings me to the end of my talk. I would like to thank you for the attention, and would like to thank the organizers for the opportunity to present here. It's pretty cool. Our research, I would especially like to thank the co-authors of this research as well. So feel free to ask any questions. Thank you.
Thank you, Derek, for the great presentation. Yeah, I really enjoyed it. And there's already a lineup. People want to ask questions. Just unmute yourself and go by the order of your hand. Maybe you can start with John. He's the top on my screen. So.
Oh, sure. Thanks very much, Derek. This is really important research. You know, as somebody who's doing this in a sort of pharma capacity, this is obviously something that I care a lot about. And I think it's really important that you put together this data set. A couple of your results, I think, are very much not surprising, which is good, right? I think that's the point. is that one is that ECFPs on like an SVM or some pretty simple classical machine learning model, given a certain split methodology that you've used here, can perform almost perfectly, but they're sort of useless in a pharma application because they can't generalize. But they're helpful for establishing a baseline here. So that's one thing. The second thing is that I think that the sort of deep learning methods that you've been using, they're not expected to perform quite as well as like an ECFP on using something like an SVM based on the sort of data limitations that you have. So I guess my question is, I don't know. Have you set up something to design a situation where you would expect the deep learning methods to perform better? This is where, I saw in your paper you use like a GIN with certain pre-training, but these deep neural networks are basically, especially the graph ones, are basically learning a worse ECFP if you have a small data set. And the consequence of this, of course, being that it's also not just a change in the molecule graph, but where the change is given a structure that's important. And I know this experiment wasn't designed to test that, but do you have any thoughts on how you could extend that, or how these deep neural networks might be able to perform better given structural information.
Yeah. So this is a pretty pessimistic view of deep learning approach, I would say. And the main reason is that we are kind of limited to these public data sets. So if you have the same situation in a pharma setting and you are able to screen a lot more molecules and curate a substantial data set with a lot less noise in it, I would assume that these deep learning methods, they would just perform way better. But yeah, that's not the reality of dealing with data that's out there, fortunately. But still, this is not the first time this discrepancy between, for example, GNNs and random forest or any other simple method has been discussed. So there are also a few papers that kind of point out the same problem, and that's that. Well, for some tasks like quantum mechanics and stuff, GNNs, they just work really, really well. But for bioactivity prediction, they're not very capable yet. So there are also some gaps in on the algorithmic side and how we deal with the data that need to be filled here to close this gap.
Yeah, thanks. I'm just going to plug again for the people on this, because this is a really interesting, research group that, again, I think there's a fundamental challenge with deep, learning and bioactivity data. Like you said, for quantum, simulation, it's been very, very successful, but bioactivity data, it's not just what, but where, and that's rarely, if ever, captured appropriately in some of these graph-based methods, but completely unrelated to the activity cliffs, which are still a huge problem.
Good, thank you, John. Pascal?
Hey, Derek, again, thank you very much for the talk. It was really interesting. And my question is more about what you gain from this research. And it's, what do you think? So based on the design, on the descriptors you use and the neural networks you use, what do you think is missing to really perform well in activity cliff prediction?
Yeah, to be very honest with you, I can't really pinpoint to a specific reason why some methods struggle a lot with activity cliff. So one of the reasons might be the data, and another part could be the algorithm that just isn't able to capture this. But what really struck me was that it also really depends on the data set. So for some cases, these very well performing strategies like support vector machining with ECFPs or another similar method performed really poorly on activity cliffs, while on other data sets they did quite well. So I think the data is really what makes the most difference here.
I'm talking about the data. Did you see any correlation, or did you see that one of the strategies you use to define similarities is correlated to better performance or worse performance?
No, I don't think I did. So we also didn't. So we had this definition based on these three types of similarity, right? We just stuck with that. We didn't look at the separate ones separately. So I'm not really sure if one of them will be way better than another approach.
Okay.
I guess not, to be honest. Yeah.
Cool. Sebastian?
Nice talk. I'm just curious to get your thoughts on is there a relationship between a model's ability and also a molecular representation ability to produce a sparse model and its ability to capture activity cliff? Is that some, yeah, just curious to get your thoughts on that.
So sorry, can you, your question wasn't completely clear to me. Maybe
yeah, my question is there a relationship between a model's ability to be sparse and its ability to capture activity cliff?
What exactly do you mean with sparse?
I mean, like sparsity in terms of, I don't know, like L1 regularization, there's many ways to produce sparse models as opposed to a dense model. If that's an area you're familiar with.
No, sorry.
Okay, that's fine, thanks.
Yeah, maybe I'm just being stupid here, but
Cool. SEM.
Hi, Derek. I remember like you had compared data set size with model performance, right? But like, do you think this could also be like an engineering issue, for instance, like earlier work with vision transformer, right? What turns out is you can't really train vision transformers well with traditional methods, right? They don't work with, let's say, SGD or RMS prop. What you need is like ADAM or like a very fine-tuned learning rate. So do you think it's the same for like molecules as well? Like do we need like clever training strategies, or do we lack something in like the model architecture itself?
yeah, so this could be a very important point actually. So for example, for the graph-based methods we use Bayesian optimization, we didn't optimize it till infinity because we have like 30 data sets and 4 different models. So we just don't have the compute to find the app. Well, of course, there is no absolute optimal model, but to optimize it really, really well. So I think there's actually a lot to gain there. But still, like you can make a support vector machine in 5 minutes. You can train it in 30 seconds. If you compare that with having to optimize a GNN for a few days, yeah, there's also quite a gap there in usability. So yeah, I'm pretty sure that we could increase the performance of some of these deep learning methods if we have a smarter optimization strategy and a bit more compute. But still, I think it wouldn't solve, wouldn't bridge this big gap.
Thank you.
Cool. Emmanuel.
Yeah, thanks, Derek, for the very nice presentation. So I have a couple of questions and comments too. So the first one is from what you presented, it's kind of obvious that the molecular representation like has a lot of impact on your result, and it for me it's kind of expected that structural like representation like ECFP would perform better than FISChem. And I have a question around like how you define activity cliff based on some form of similarity, but using representation like ECFP for that. But then in your training set, you were still using ECFP for measuring the performance. So yeah, it's kind of like I feel like there's might be some form of bias there, but yeah, just a small comment. And my question would be like, have you tried to look at what happened when you use things like deep neural network, but using supplementing the representation with fixed representation that you get from ECFP, for example? So like when you compute your, for a graph network, for example, when you compute your global pooling, you may add some concatenation or some form of like another way to add the information from the ECFP. And do you think that could maybe be a way to like improve the performance of this kind of model in the context of activity cliff?
Yeah. So first of all, the second point, very fair comment, that there might indeed be some data, some bias in there. And then for the descriptor-based methods, that it's obvious that they perform better. Well, you could also look at it from a different perspective. So, for example, we know that 3D information could play a big role in activity cliffs, and you have this WIM descriptor, for example, that describes the 3D structure of a molecule as well. So maybe that would be a lot better than other approaches, right? So to me, it isn't obvious that these ECFPs would also be better on cliffs per se, even though we know that they are better just like overall. And then the third comment, adding like external information like ECFPs to the deep learning approaches. This could be interesting, but it's also a bit besides the point of deep learning, right? So what you're trying to achieve is that you learn directly from the molecular representation without doing a lot of feature engineering, because you saw, for example, with images back in the days, it was just feature engineering and then some more feature engineering, and then you applied support vector machine, for example, until CNNs came around, and at some point feature engineering just didn't work as well as running directly from the data. And that's something that you also would like to achieve over here, right? So you would hope that that these deep learning methods, they could just capture the molecular structure as is without doing a lot of feature engineering. So maybe in the short term it would increase performance, probably, but at the end of the day, I think it's a bit besides the point of using deep learning.
Yep.
Tariq.
Hi, everyone. Thank you for the great presentation. I have a very quick question. So did you measure any metrics from what's happening inside the neural networks that could explain maybe they're not converging as good as one might expect?
Yeah. So during training, during training we didn't see any weird things going on. So they all just seem to converge well. Okay. Maybe I missed something, of course, but it seemed to be just like a normal, basically.
Okay. Because my question is related to the graph you showed where you had the MLP and the SVM at the far right, and you had all the other networks on the other side. And from what I remember, you had some of the deep neural networks you've shown have a very large standard deviation.
Yeah, over here. Yeah.
Yes, this one. Yeah. So maybe, I mean, when I'm looking at this graph, I'm thinking maybe there's something happening with the gradient descent. So maybe you have some spikes, maybe you have something that might explain that some networks can go completely off and the other ones can converge really well. And so that's what my question is about. Actually, it's like, do you see anything weird in the gradient, for example, when you look at this, for example, the TCL or GOT?
I didn't see super weird behavior during training, but then again, we were training like almost 200 neural networks and optimizing each of them, of course. So we've trained a lot of networks, so there's a chance that I missed some weird things going on, but I didn't notice them.
Okay.
Good. Yeah.
Okay. Thanks a lot.
Cass?
Yeah, maybe one last question. I forgot how exactly you split your train from test, but could it be that this somehow could this be considered an out of distribution split? Like, does it somehow maximize dissimilarity in a way?
Yeah, so we of course we try to minimize out of distribution in our splitting approach. So I don't think that that's what's happening here. But yeah, as I mentioned, it's pretty difficult to separate these cliffs between train and test, because sometimes molecules, they have cliffs with 10 or 20 different molecules, right? So it could still happen even with trying your best.
So are there some measures of, like, do you have some measure of similarity between train and test, or did you not get to that, or do not?
No, I didn't. But it's actually a thing we should do, actually, I think. So thanks for reminding me. Yeah, it's probably important to check that.
Cool, thanks.
Cool. Maybe I will ask one or two more questions before we end this. So in the split that you did you consider maybe the difficulty of the task based on whether we have seen some activity cliff in the test or not? Like, so my question is coming from the perspective, if I haven't seen any activity cliff in the training set, then it will be hard for me to generalize, right, to new activity cliff in the test set. If I haven't seen a lot, maybe it'd be easier. So did you consider kind of those settings where you actually maybe vary the percentage of activity cliff that has been in your training set compared to the one you have seen in the overall data set?
Yeah, so the activity cliffs are pretty common in all of our data sets. So there are a few with not that many in them, and you see a bit more variation in these data sets, which is not that strange, of course. But for example, if we try to change the definition of activity cliffs we use to make activity cliffs very extreme, then they become a bit harder to predict. I think that's also pretty logical. And if you make them very soft, basically the definition, then they become easier. So yeah, it does depend on that. Yeah, but I would say that we try to use a sensible definition of what an activity cliff is, and we also try to have a good distribution between the train and test of activity cliff compounds. So we try to minimize the effects of that.
Okay, I see. Thank you. And what about so here in this study, you kind of consider all type of activity cliff as being the same, but we know that when you measure the activity of a compound, as you get more senior, there's less noise on the measurement. So in low activity regime, like kind of you just consider splitting the activity cliff based on like kind of the actual activity, initial activity, maybe like in low activity regime, the model behaves more or less differently than in high activity regime. Like.
Yeah, so we didn't try this. And one of the reasons is that we use a 10x difference as a kind of a threshold, right, for our definition of activity cliff. So that automatically reduces the number of activity cliffs in a very high bioactivity region, because if you have a model that has a 100 nanomolar bioactivity, then you have to have a cliff molecule that has that 10x. So those are less common. So I would guess no, but we haven't checked that explicitly.